And we are going to add the technique of factoring. What we did at the beginning of this unit can be really helpful for graphing. If we can find all the x-intercepts, all the y-intercepts, and the end behavior, we're going to be able to draw a fairly accurate graph. So what does that look like? Well, this is one that you could do even before Chapter 1. This you could factor last year in grade 11. And the reason we can factor this last year in grade 11 is because it has a common factor. I could take out an x. And if I take out a common factor of an x, then I have a quadratic, which I can also factor from my grade 11 skills, even grade 10 skills, plus 3 and minus 2. And if it's factored, anytime it's factored, you can find x-intercepts. How do we find x-intercepts? We plug in 0 for y. And if we plug in 0 for y and it's factored, those are the three numbers that would make it equal to 0. Okay. Now, before we factor in a question like this, we go back to some of the stuff that we did in question 1 that we already knew. You already know the end behavior. This is an x cubed. It's a positive x cubed. It acts like a line. You would already know that as your end behavior. What also would you know? Plug in 0 for x. You would get 0, 0 as your y-intercept. You would know that already. So to start off with, we would know this point, and we know the end behavior. We just added the fact that we know this point and this point as well. So if my end behavior starts down here and ends up here, and I draw a smooth curve between those points, this is the expectation in grade 12 for graphing. Where do we have inaccuracies? We don't know exactly how high or how low it goes as a local max or a local min. We're going to need calculus next year to find it, right? But if you wanted to use your math this year to be more accurate, you go back to the basic computer idea, right? What numbers might tell us how high it goes? Oh, plug in minus 2, plug in minus 1. See where they go, right? If minus 2 and minus 1 were up here, you'd be like, oh, it kind of looks like space. Anyways, you would say, I should have gone higher in my graph. And if you plugged in minus 1 and it was down here, like, oh, I should have gone lower. But for grade 12, they're okay if you have just your x-intercepts and y-intercepts and your end behavior correctly. If we just have our x-intercepts and y-intercepts correct and have a smooth curve going through them, they're going to be like, you have the basic idea of what this graph looks like. Now sometimes, and we're going to look at the example that the notes has finished for us as well. Here they're saying, sketch this graph, and we're going to use the x-intercepts and y-intercepts. Well, preliminary, I would know my end behavior in this one. Acts like a parabola. It's positive leading coefficient. I know that that's my end behavior. And the other preliminary thing I would know already is that if I plug in 0 for x, I love this mental math. Like, okay, probably don't take this long, do you? 0 to the 4 times 2, 0. 0 cubed, 0. 0 squared, 0. Times negative 14, 0. 19 times 0, 0. And all of those will be 0, and you're just left with minus 6. The y-intercept is so nice and easy to find. Okay? You know what the exam likes to do, though, to check if that you really understand a y-intercept? They'll give you a question like this. And say, what's the y-intercept? And sometimes as students, we get caught seeing a pattern that, oh, it's always the last number. Well, it's always the last number if all the other ones are 0 when you plug in x equals 0. The idea is still you have to plug in x equals 0. What's the y-intercept of this one? 10. Because if I plug in 0, I still get 3 squared, which is 9. Plus 1 is 10. Okay, so be careful, because the exam will be like, every once in a while, be like, hey, can you find the y-intercept for this? And they will definitely, in the multiple choice, put the plus 1 there to tempt you. Because you're going to get used to so many times saying, hey, it's just the last number. It's just the last number if it's a polynomial written this way, where everything else, when you plug in 0, becomes 0. Okay, so that's what we know already. We know the end behavior, we know the y-intercept, and we are going to use our new unit and our new skills of factoring. So if I was factoring, first of all, I would look at my last number. And I would say, if this factored, it has to be a 1, a 2, a 3, or a 6. Those are my only choices for factors. Positive 1 or negative 1. So the textbook tried some stuff. They found out that if they plugged in 1, they got 0, which means x minus 1 is a factor. They did the synthetic division, and they wrote the division statement here. Right? What are some of the things that we did? We usually said, they're using f, so let f of x equals, we usually started with p of x. It doesn't matter what letter we use for our function. So that would save us some time, because we could say, so p of x, or f of x, equals this. And now, in the purple box here, we still have an x cubed. So we have to factor again. And in factoring again, they found another number that made it equal to 0. They did the synthetic division, right? When they found out that, so they found out x minus 2 was a factor. They did the synthetic division, and they wrote their division statement again. Now, their division statement, again, still had the original function. So this is where it's nice to have f of x or p of x, so you don't have to rewrite all of them. F of x equals. They still had the original factor, but now they added the x minus 2 factor and had the 2x squared plus 5x minus 3. And once we get to a quadratic, we can factor easily. And once we factored completely, we find a whole bunch of x-intercepts. X equals 1, x equals 2, x equals 1/2, x equals negative 3, and we have our y-intercept at negative 6 already. This is enough to draw the graph. We'll skip all this, get to the graph part. So on the graph, we would label negative 3, 1/2, 1 and 2, and we would label the y-intercept. You would know that your end behavior opens up like a parabola, so it's going to have this at the ends. Now, if you were graphing this, this is what I would expect would happen with you. We don't have patience. You would be like, oh yeah, there we go. That's the graph you would draw, full marks. It could, and apparently it does, go down a lot lower. But you connected dots like in elementary school, remember those drawings? And you always had to use straight lines. So now we're using connecting the dots with curved lines, but it's very hard for our brain to be like, no, I want to go the shortest way possible. So you will loop down. Now you want to make your curve smooth, okay? So I'm going to show you what connecting the dots with your curve should be smooth. If you start your curve smooth and it's not the right curve, something bad's going to happen. For example, this. I'm starting here, I'm like, I want to go to this one. Now it's smooth, right? Can you see? Whoa! Oh my goodness. Like, the smooth curve, if I wanted to keep going smooth, it felt like I had to go back in time. That's going to be bad. You're going to lose marks for that. So I need to go through all of these points with a smooth curve. So in order to get this, that is a better curve. Because then I'd have to go lower in order to swoop up nicely to go through the next points. And obviously, right, we don't know that minimum point yet. So how high or how low it goes doesn't matter. We'll leave that for calculus for next year. But you can circle questions 7 and 13.